Okay, so now we're going to talk about the inverse Laplace transform. We talked about taking an equation for our DC motor. We had the basic Kirchhoff's laws, Newton's laws, things like that. Put that into an ordinary differential equation that we transformed into Laplace domain. Here's our Laplace domain transfer functions. Our output omega of s is a function of the input v of s and is a function of the initial conditions, all in Laplace domain. Now we want to be able to work with this in time domain and perhaps even create a function as a plot as a function of time or something. So we want to do the inverse Laplace transform. Now to do an inverse Laplace transform, I could do it directly on initial conditions, but I'd have to have initial conditions specified. I can do it on the response to an input, but I have to know what that input is because I'm doing it in time as a function of some input. We're going to do this right now as a function of the input, and so I'm going to erase this portion. We'll just assume that the initial conditions were 0. If they weren't 0, I could do these two transforms separately and then add the results together at the end because, again, we're assuming a linear system, so we can do that. So we want the time response to an initial condition. We'll assume that V of s, or V, not V of s, Vs, our source voltage, equals 12 volts at time greater than or equal to 0. So basically at time equals 0, we input 12 volts. That's an at and times at and time greater than 0. So we're assuming a step input at time equals 0 of 12 volts, and this is very close to what we modeled in the DC motor examples we were using, so that makes for a good example. In Laplace, take the Laplace transform of that, we get Vs of s equals 12 over s. Okay, so I can substitute that into here, 12 over s, and I can substitute in all of these numeric values for the various values here, and when it's all said and done, I get omega of s equals 15,000 times 12 over s squared plus 500 s plus 255 times s. Okay, and if I wanted to multiply that out one more step, that would be multiplied by that s. This would be an s cubed, an s squared, an s there, plus 0s. Two ways I can do this. I can do it by hand, or I can throw it into MATLAB. But before we get into that, I think it helps if we know where we want to go, right? I'm going to factor this out somehow, probably a partial fraction expansion or something. But where do I want to get to? What are the things I'm looking for after I factored it? Common things, 1 over s. That's equivalent to just 1 in time domain, function of time. If I have a constant, k over s, I get k. Okay. 1 over s plus a is a common one, and that transforms into e to the minus at. And again, if there's some constant k here, there's a constant k there. It's not a problem. S over s squared plus omega gives us cosine omega t. Omega over s squared plus omega leads us off to sine omega t. And these are just, the things that you find typically at the front of a Laplace transform table. There's one more I want to play with a little bit here before we get back to this problem. Because it's kind of a handy way of factoring things. If I have omega over s plus a squared plus omega squared, that transforms into e to the minus at sine omega t. Okay? And this is actually common where you have complex roots and things like this. You can factor it this way. And let's take an example, a simple example, just to see how this works, and then we'll get back to our main problem. So let's suppose I have my transfer function is 8 over s squared plus 10s plus 41 that came from whatever. Okay, that's equal to, how do I factor that denominator? It's going to be a messy one, right? So I can factor it as 8 over s plus 5 and plus 16. Okay, because s plus 5 squared, s plus 5 squared, I'm sorry. So that's s squared plus the 10s plus 25. Well, I've got 41, so I have my 16 left over. I can, to get that into this kind of form, I can say that is 4, since 16 is 4 squared, over s plus 5 squared plus, I'll write it as 4 squared, right? And then that whole thing, because I really needed an 8 there, times 2. Okay? So I can take that and do the inverse Laplace transform. Now, my 2 is just a constant, so I get 2 e to the minus a is 5, okay? 5 t sine of my omega is 4 t. That's an equals, not a trans. Yeah, so that transforms to just like I drew. So there's my function for whatever in time domain. Okay, that's kind of a funny way to factor things, but it works out conveniently when doing this kind of problem. But given what I've got here, I'm going to let MATLAB do the heavy lifting. We'll just show you the MATLAB commands to factor this, and then I'll go through and actually do it by hand. I'll cheat a little bit and change these numbers and make things come out integers, just so I don't have to carry a lot of fractions. But let's start with the MATLAB. In the command, so here's my transfer function. Command to factor this and find the residues from our partial fraction expansion. I will give it RPK. The function returns 3 different vectors: the residues, the poles, and the direct terms. Equals residue, all lowercase, of course, of, I can give it the numerator like I always have. My numerator is 15,000 times 12, and I give it my denominator, which is 1 times s cubed plus 500s squared plus, or not plus, comma, 255s, comma, 0, not an s there, it's just a 0. Carry away. Yes. I have to give it that 0 so that it knows there's no constant term. Otherwise, it would have just assumed if I just put these terms, it would assume that it's a second order equation, not a third order equation. And MATLAB comes back with R equals 0.7219 minus 800.7219 and 800. That's my residues. And this is why I'm going to cheat when we do it by hand, so I don't have to carry all these fractions. P, and it reports these as a vector, column vector. P equals 499.5496 minus 0.4504 and 0. Okay? So those are my poles. And my direct terms, K equals an empty vector. Okay? And you get an empty vector as long as the order of the denominator, the power of S or whatever in the denominator, is less than the numerator. You end up with an empty term here. So to take those numbers and put them into a useful form, I would say that my omega of S equals my first term. I have a residue in my partial fraction expansion, 0.722 over a pole, S. Now, my pole is minus, okay, minus 499. My pole is minus 499. My denominator is going to be S plus 499 point whatever. My second term, I have minus 800.72 all over S plus 0.45, and I'm leaving some decimal points off here. The third one, I have plus 800 over S plus 0. Okay, so we can need to write that. So that's my partial fraction expansion. Okay, I can take each of these terms and do the inverse Laplace transform out of our tables. 1 over S is a step function. These terms erase that. So 1 over S equals a step, or just a constant. So 800 over S is just going to be equal to 800, right? These terms are going to be something, K times 1 over S plus A, and whatever K works out to be, the numerator, and that will transform into K times e to the minus AT in our tables. Okay, so let's actually put these together, and I get omega of t, what I want in response to step, equals 0.722 e to the minus 499 point something t minus 800.72 blah 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 e to the minus 4.5 t plus 800. Okay, kind of messy, but what does that look like in our graphically? Well, again, it's a linear system. We can look at each one independently. If I have my out function of time, this is output, omega. Oh, I need to do this. This is 0, and this is t. My first term is 7.22 times e to the minus 499. So this is a fairly large term in my exponent. It's negative. This is going to go away quickly. It's going to start out small, and I'm going to get something like that. Second term, I got 800 minus 800, that's a big number, times e to the minus 4.5, so that's much smaller than 499. That's going to last roughly 10 times longer. So if this one lasted this long, that one's going to last that long. It's going to start at minus 800. And it's going to fade away like that. And I have my constant term of 800. It's constant like that. And when I put all of them together, I end up with a response where, you know, this 800 and this 800, minus 800 point something, and that we start at about 0, and we end up kind of like that. It's not very well drawn. Well, now you know why I'm an engineer, not an artist. Assuming I haven't used that joke already. So you end up with a final response looking something like that. Okay? Now, how would we do this by hand? Okay? We have some idea where we want to go. We want those 1 over s's and the 1 over s plus a kind of things. So we're going to do a partial fraction expansion, and with me, I'm going to. This is where I said I was going to cheat, because I don't want to deal with 499 point this and you know. So we're going to make this come out to round numbers. I'm going to make this 500.5. And I'm going to really cheat on this one and make this one, well, that's not 255, that was a 225. I made a mistake in my notes there. So I'm going to make it equal to 250. So in the previous conversation, you know, anywhere where I said 255, to make that 225, the results are the same. Okay, I did that because then it becomes easy to factor here. So I've got 18,000 over, or 180,000, excuse me, 180,000 over s plus 500 times s plus 0.5 times s. Okay, so that's how I factor that out. And our partial fraction expansion tells us that that's going to be equal to some constant a1 over s plus 500 plus a2 over s plus 0.5 plus a3 over s. Okay? Now, all we need to do now is go through that thing and factor things out and find out the values of A1, A2, and A3. So our process in general, I need some room. I'm going to erase all this. Our general process is, if I have some numerator function and I have a series of poles, s plus p1, s plus p2, all the way to s plus pk. Now let me throw in an s plus pn in the middle. S plus pn s plus pk, all multiplied together. Now I'm going to have to erase my motor. You guys should remember that picture by now, right? I hope, equal to A1 over S plus P1 plus A2 over S plus P2 dot 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 AN over S plus PN dot 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 AK over S plus PK. K poles, okay? What I want to do is multiply the whole thing by S plus Pn. So I'm going to eliminate Pn. So both sides, S plus Pn, which is going to cancel this, S plus Pn, S plus Pn, S plus Pn, S plus Pn. And I'm going to evaluate that at S equals minus Pn minus Pn, okay? Now the first thing I notice is that here in my nth term, S plus Pn cancel, leaving me with just An. Which happens to be the thing we want to find. Now when S is equal to minus Pn, this is equal to 0, this is equal to 0, this is equal to 0. All these terms go to 0, and all I have left on the right-hand side is An, and I have on the left-hand side everything except for this one pole, and I can substitute S minus Pn into each of those terms into the denominator, and I get something that is equal to A sub n. Okay? That is the process. And let me move my equation up here on 80000 over S plus 500 S plus 0.5 S, that's, S plus 0, our pole is equal to 0 there, equals A1 over S plus 500 plus A2 over S plus 0.5 plus A3 over S. I just need the room. So, start out with, I'm going to look at finding A1. So I'm going to multiply both sides by S plus 500. So I get S plus 500 times 180,000 over S plus 500 S plus 0.5 S. And on this side, since I'm going to evaluate this at S equals 500, or minus 500, excuse me, I know that when those S plus 500 terms are going to make those go to 0, and all I'm going to have left over here is A1. I'm just going to write that directly rather than doing all that. This cancels with this. So now I have 180,000 over S plus 500 divided by 100. I'll write that out. 180,000 over S plus 500. Not S plus 500. Come on, I'm evaluating it at S equals 500. I get minus 500 is my S term here, and this one here is minus 500 plus 0.5. And that's A1, and that comes out to be 0.7193. Not exactly the answer we got before because we had cheated a little bit and rounded things out. For number 4, I'm just going to write this directly. A2, because I know that this term and this term are going to go away, and all that's going to be left here is A2 equals, and we're going to evaluate this at S equal negative 0.5. This is going to cancel out when I multiply through by the S times 0.5, so we'll be left with 18,000. I'll write it out. S plus 0.5 over S plus 500, S plus 0.5, S. So this and this cancel out. I evaluate that at S equals minus 0.5. And I get an 8,000 over minus 0.5 times 499.5 equals 720.72 is my A2. And A3, my S term is going, I'm going to multiply everything by S again, evaluate it at S equals 0. So when I multiply by S, that'll cancel that out. When I evaluated S equals 0, S times that is going to be 0, S times that is going to be 0, and all I have left here is A3 because the S and the S will cancel. And on the left side, I have 180,000 over S plus 500 plus S plus 0.5. S is equal to 0, okay? So I end up with 0.5 times 500, so that's 180,000 over 250 equals 720. Okay? Not quite the same result, you know, we got by MATLAB, but that's because I tweaked these up a bit just to make things a little easier to write and not have to carry a lot of decimal places. So I have A1, A2, A3. I have my poles, minus 500, 5. Well, I have my partial fractions and denominators. Okay, I've got this, this, this. So I can say that omega of S equals 0.719 over S plus 500 plus 720.7 over S plus 0.5 plus 720 over S. Transforming those into time domain just like we've done before, I get omega of t equals 0.719 e to the minus 500t plus 720.7 e to the minus 0.5t and plus 720. And that gives us that same response we saw before. The time constant slightly different, final value slightly different because of the round-offs I did. But it's the same process. So it's tedious, it's time-consuming, it's a lot of screwing around, but there's nothing mysterious about it. Okay.